So, hello everyone. We will be continuing with the topic of phasor diagram for a practical transformer. Last time we have not considered R1, X1, R2, X2 while drawing the phasor diagram, and this time we are going to start with the phasor diagram for a practical transformer. So please draw. I mean, if you wish to draw, you can draw the circuit again, or else you write the relationships, which I'm going to show you all. So up to your wish, you all can show the diagram. Uh, Facing. Till that you draw the equivalent circuit, please. Draw the equivalent circuit. Okay. So here, if you see carefully, I am facing a lot of problem with the writing pad. I have to somehow make it work for the lecture. Okay, hopefully this works now. Yeah. So how do I write this equations? Let us start. I have to write the equations for V1, E2 and I1. I1 I already know. I1 will be given by I0 plus I2 dash. Yes. There's no need to explain. This is there. Then the second equation is of V1. V1. So what is V1? I1 into R1 plus I1 into X1, and here it will be minus E1. Yes or no? Because V1 and E1 are related by same polarity, I mean opposite polarity but equal magnitude. So this is the relation, right? So V1 is I1 R1 plus I1 X1 minus E1 bar. Agree? What is E2? E2 is I2 R2. Now the current is flowing outward, so we are measuring E2. It is I2 R2 plus I2 X2 plus V2, because E2 and V2 are of the same polarity. So it will be I2 R2. This is one. I2 R2 is there. Drop voltage drop. Then I2 X2 plus V2 bar. Agree? Hello? You have written these three equations.
Yes, sir.
Okay. Now, when the load is resistive, that is for the case of unity power factor, we assume that K is 1, the transformer ratio is 1, so E2 will be equal to E1. That is for sure. We have a reference flux. Phi is the reference flux. Okay. Phi is the reference flux. And we assume that your phi flux leads E1 and E2 by 90 degrees Celsius. This is the assumption. The flux leads V1 and V2 by 90 degrees Celsius. And phi 2 is 0 because there is a resistive load. So phase difference between I2 and V2 is 0. Okay. So phi 2 is the phase difference between I2 and V2, which is 0 degree because of the resistive load. So can we start now? So we have to write those three equations which we have seen just now. That is V1 bar is equal to I1 R1 plus I1 X1 minus E1 bar. Okay. Then E2 is V2 plus I2 R2 plus I2 X2, and I1 is I0 plus I2 bar. Alright, and we have already seen that E2 is equal to E1, and what about, yeah, V1 is there, V2 is there. Okay, fine. Here we cannot say V1 is equal to minus of E1. It's not true because related by this equation. Last time this R1 X1 was not present. So that's why V1 we could have written minus of E1, and E2 we could have written V2. But here it is not the case. Okay. So be careful on that front. Now your phi flux phi leads E1 and E2 by 90 degree. Okay. So let me draw a reference phasor. So this is phi, this is phi. So what have we said? We have said that E1 and E2, phi flux leads E1 and E2 by 90 degree. So where should be my E1 and E2? Can you tell me? Leading now. So where it should be? Hello. Flux phi, it's leading. So can you tell me where it will be?
Y-axis.
Yes. Y axis below or above?
Above.
No, below na. Phi is leading. Flux phi is leading E1 and E2, right?
So it's leading. So
Phi is leading. Yes or no? Phi is leading E1 and E2, na? So it cannot go up. Up means E1 and E2 is leading phi by 90 degree. So this is clear. And E1 is equal to E2. Correct?
yes.
Ha. Now, now what do we do next? How do we proceed ahead? Yes. How will you draw other cases? So this is E2 equal to E1. E2 equal to E1. Now we'll draw I naught. Where will I naught come? Or where will rather I? Yeah, tell me.
First quadrant. Reference line के just above.
This way, right? I naught bar. But I mean, we should also determine where should I2 come, right? I2 and then correspondingly other things. Acha, where will V2 come? V2, where will V2 come? Any idea? Hello.
No idea, sir.
Okay. Yeah. So I2 and V2 should have a zero phase difference. That much you agree?
Yes.
Ha. Now let us draw. Let's say it's an resistive load. Okay. Phi is a reference node. K is equal to 1. E2 is equal to E1. That we have drawn already. So this we have already used. Now I1 is basically I naught bar plus I2 dash bar. Okay. So we know that I2 dash bar will be somewhere around lesser than this only. So let me draw it over here. Let's say it's over here like this. Now how will you complete this? By parallelogram, right? Yes or no? So the resultant will be what? What will be the resultant? I1 bar. Yes or no? And this will be I2 dash. So where will be I2? Yes or no? This will be I2 bar. Agree? Hello?
Yes, sir.
And I2 and V2 direction should be same. So I2 V2 direction will be on the same line. So let's say this is V2. Now tell me what will be, where will be I2 R2? Where will be I2 R2? I2 will be on the same line, right? V into I into R. That will be voltage drop, which will have a no phase shift. So this is phi 2 which will equal to 0. So if I extend it further like this, so this part will be I2 R2. This voltage drop, this one. Okay, on the straight line. If we consider this on the same part, okay, let me continue on the same part. So let's say this is V2, okay, and this ahead, if I extend it ahead, this part becomes I2 R2. Okay, now tell me where will I2 X2 come? Hello, can you tell me? So I2 R2 I have drawn. Now I have to draw I2 X2. What is the relationship between them? This is an inductor. So the current flowing to the inductor and current flowing to the resistor, which one leads? I mean, it will have a relation of. It's a pure inductor. Okay,
Lags behind.
90 degree, na 90 degree.
Yes, sir.
Huh. So you drop a perpendicular from here to here. This is 90 degree. This is 90 degree. Okay. So drop a perpendicular from here to here, and then you can extend this. So this line will be. So this line, this will be I2 X2. Agree? So this, if I extend it further, this is your E2. E2 equal to E1. Initially E2 equal to E1, I didn't knew the magnitude. Agree?
Yes, sir.
So yeah. So this is how I have to plot it. Then so what is the first step? I have drawn E2 and E1. Then I0 not we have drawn. Then I2 dash. Then I1. Then I2 opposite we have drawn. I2 dash opposite we have drawn I2. Then V2. Then I1 I2 R2. Then I2 X2 will be opposite of 90 degree. There is a 90 degree phase shift. Okay. So we have dropped a perpendicular over here 90 degree, and whenever it touches this is E2. So what is this E2? E2 consists of what? Can you tell me? E2 consists of V2, right? Plus I2 R2 plus I2 X2. Correct it is? This is equal to E2. Agreed now? So V2 is V2 plus I2 R2 plus I2 X2. Do you agree this? Agree on
Yes,
this?
sir.
Ha. Now tell me where will opposite, we have to draw the opposite now. Above E1 V1 we have to draw V1. So V1 also will be a sum of three things. It will be I1 R1, I1 X1 and minus E1. Yeah, tell me how to draw it ahead. Where will this thing come? V1 and V2. Sorry, yeah, E1. Minus of E1 कहाँ पे आएगा बताओ? If this is E1,
Positive wire.
yes, same magnitude, yes.
Yes, sir.
So same magnitude you draw it up, and that will become your this thing minus of E1. So similar magnitude I'll draw it over here. So what is this? Minus of E1, correct? Yes or no? Now where will I1 R1 come? See, I1 already direction is there. Okay, if I draw a parallelogram like this, but I don't know magnitude. Magnitude, this will be I1 R1. Like, let's say this much is the magnitude. Okay, now how will I draw I1 X1? What is I1 R1 and I2 I1 X1 relation? 90 degree, right? Yes or no? So what I will do, I'll take a line and draw 90-degree line. 90 degree from here, drop a perpendicular to 90 degree. Here it is. Let's say I drop a perpendicular to 90 degree like this. Okay, so this is 90 degree. Yes or no? This is I1 X1. Okay,
Yes.
and then where will your V1 come now? So this is minus E1. This is I1 R1. This is I1 X1 bar. So where will my V1 come? This one from here to here. Agree? So this will become my. I have to draw a straight line passing through this one. So this one is my V1 bar. Agree now? So V1 is what?
Yes.
V1 is I1 R1 plus I1 X1 minus E1. Okay, so this is all the three are satisfied now. So we have determined E1 and I1. So what is the phasor angle between them? E1 and I1. This phasor angle is phi 1. Where is E2 and V2? Phasor angle is 0 degree. And where is the phasor diagram between I naught and V naught? I naught and V1, sorry. So I naught and V1, this one. This one is my phi 0. Okay, so these three you have to show, and this completes the diagram. Please draw it now. I hope you have followed this. So this completes the phasor diagram for when the load is resistive, unity power factor. Have you completed? Hello students, did you all complete it?
2 minutes, sir.
Okay, okay. We have two more phasor diagrams. When the load is inductive, that is lagging power factor, and next one will be when the load is capacitive for a leading power factor. If you draw by scale, then everything will come properly. I have drawn by hand, so it's coming little bit this way. But if you draw it proper 90 degree and all, it will come in proper manner.
Sir, completed.
Everyone else completed?
Yes.
Okay. Now we'll go to load is inductive. That is lagging power factor. Yeah, what is the difference now? Due to inductive load, current I2 lags behind V2 by an angle less than 90 degree. Okay, it's not a practical inductive load, so it will be having an inductive and a resistive. So that's why phi will be less than 90 degree. Okay, phi 1 is the phase angle between V1 and I1. Phi 2 is the phase angle between V2 and I2. This will be less than 90 degree. Okay, can we start? And we assume that E1 is equal to E2. So what are the equations we will write over here? You have to write those equations. V1 is I1 R1 bar plus I1 X1 bar minus E1. Then the next relation is E2. E2 is I2 R2 bar plus I2 x2 bar plus V2 bar, and I1 relation is I1 bar is I0 plus I2 bar. So with that, let us start, and we will assume that phi has a flux. Phi 1 is leading E1 and E2 by 90 degree. That is the assumption. Okay, this is phi. So E2 and E1 will be over here. Maybe we don't know the magnitude yet, but it will be E1 equal to E2. Here it will come. Alright. Now, how to start? Again I repeat. First we have to identify where is I0. So I0 is over here. Then somewhere around here your I2 dash will come. Correct? Then we draw the parallelogram. We draw the parallelogram and complete this. So here what will come? Tell me. I1, right? Here I1 will come. I1 bar. So this is done. Sorry. This is completed now. Let me open this PDF again. Yeah. Yeah. So I've completed this much. Now after that what will happen? Tell me. Where will I2 come?
Reflection of I2 dash.
Yeah, behind. The same here, the same behind. Like this. Exactly behind and the same magnitude, right? Like this. Same magnitude. This way. Where should V2 come now? V2 should come to the right or to the left or below or above? I2. I2. This is I2. Whether it should come below or above I2.
Above I2.
No. Why? Because I2 is lagging
No,
behind V2.
current
No.
is lagging behind, no? So V2 will come up.
Current is lagging behind V2. Inductive load. Yeah. So where it will come? Here. It will come below, right? Because it is first. Do you agree? Yeah. See, current will be here, voltage will be here. Did you understand how? And this is phi 2. Current is lagging behind now, so voltage is first in this quadrant.
Okay.
This is behind and this is first. So this is phi 2. Now tell me where will this come? What I say I2 R2? I2 R2, come on. Where it will come? It will be a line parallel to I2, right? Yes or no? A line parallel to I2. This is I2 R2. Agree? And
Yes.
then drop a perpendicular over here. You will get what? drop a perpendicular here. Here you will get I2 X2. Okay, and this line will be, draw this line as E2 or E1. Okay, so please complete this. So what is E2? E2 is I2 R2 plus I2 X2 plus V2. So this is V2. So E2 will be V2 plus I2 R2 plus I2 X2. This I2 and this I2 R2 direction, I mean, this thing is same, angle is same. So it will be parallel. Do you understood how to draw it? Did you understand? And then 90 degree from there, draw a line. Wherever it intersects this becomes my E2 equal to E1. Have you understood this?
Yes.
Yes.
Okay, now that we drew our tension above. So where will I draw minus of E1? Above, right? Reflection of E2. So that will be minus of, so this is minus of E1. This and this is same. Okay, now tell me where will I1 and I, this will come now, tell me. So I1 will be in the same direction as this, right? Correct now? I1 R1. This parallel to this now. And then 90 degree above, you take a 90-degree line and draw this. This is 90 degree. So this will be I1 X1 bar. This is I1 R1 bar. So where is my this thing now? Hello? Where is my V1 now? Will be here, from here to here. Okay? This is I1 X1. This is I1 X1. This is I1 R1 and this is E1. So here this will be V1 bar. So V1 bar is what? I1 X1 plus I1 R1 minus E1. Do you agree on this? Did you understand? So this remains the same. So due to inductive load, the current I2 lags behind voltage by an angle less than 90 degrees. So this is phi 2. Where will be phi 1 now? This one, from here to here. Okay, this is phi 1. Where will be phi naught? Phi naught is the angle between V1 and I naught. Here, this will be phi naught. Okay, so phi 1, phi naught, and phi 2 we have drawn, and we have also drawn E1, E2, V2, I2 R2, I2 X2, I1 R1, I1 X1, and V1. Understood?
Yes.
Yeah. If you have still confusion that why V2 is coming below I2, remember this is the third quadrant, and in third quadrant we have negative. So negative में this is more negative, so that's why it is less compared to this. Now understood? So can we move on to the load capacitive now? Everyone completed this, or you require some time?
Yes, sir, completed.
Okay, I hope it is looking the same way as I have drawn over here with pen, with scale and pencil. Okay. So now we draw again the phasor diagram when the load is capacitive. That is a leading power factor. So again we write the three equations. V1 is I1 R1 bar plus I1 X1 bar minus E1 bar. V2 is I2 R2 bar plus I2 X2 bar plus I think here this is E2, right? E2 is this plus V2, and then we have I1 bar which is I0 plus I2 dash, and we have E1 as same as E2. So let us start with that assumption that reference phasor leads the this by 90 degree. E1 and E2 by 90 degrees. So E1 and E2 let us draw here. So this is E1 equal to E2. Let me start now. So first I'll draw I1 which is I0 plus I2 bar. Okay. So let us do that. So this is I0. Let's say this is my I2 bar. So if you draw the parallelogram now, so this will be I1. I hope you are following and doing along with me. This is I1 bar. Okay. Now what we will do, I2 we have to draw. So I2 will be the mirror image down, right, of I2 dash. So I'll extend it down. This is I2. So since it's a capacitive load, current will be leading the voltage by 90 degree. Current will be leading, but it will be down. So where will be V2? V2 will be around here. Yes or no? Because current is leading the voltage here. So this is phi 2. Agree? Now, where will I draw I2 R2? Come on, tell me. Bolo. So there will be a,
Parallel to I2.
yeah, parallel to I2, there will be a line like this. So this will be I2 R2. And where will I draw I2 X2? Yeah, drop a perpendicular, na?
Perpendicular to I2 R2.
Yes, so perpendicular to I2 R2 somewhere around here. So this is 90 degree. This should be 90
Yes.
degree line. And wherever it intersects over here, this becomes E2. That's why I'm not drawn its proper this thing. Yeah, this is where they will meet. Somewhere around here. Okay. So this is E2 equal to E1, and this will be I2 X2. So your E2 bar E2 bar is V2 plus I2 R2 plus I2 X2. Agree? Can we go up now? So above we have E2. So sorry, E1. That is same as E2. So if I want to draw minus of E1, then same distance I have to draw up also, right? So same distance I'll draw it up. That will be minus of E1. Somewhere around here. This minus of E1. Agree? Now what I will do? Tell me. Come on. Parallel to I1, right? I'll write I1 R1. Then what I will do last? Tell me fast.
Perpendicular to I1 R1.
Yes. Perpendicular to I1 R1, I'll draw a line. Okay, very good. Yeah, yeah, like this. So this is I2, sorry, I1 X1. I1 X1. And from year to year, I will draw that, join that line. Let me use black color. Okay, we start from here. I have to draw a straight line almost, so please draw it perfectly in your case. In my case, it will take some extra effort to draw it straight line. Maybe now it will come. Yes. So this line is what? What is it? V1. So this is V1 will be equal to I1 X1, I1 R1 minus E2. Okay. And this completes the phasor diagram for a capacitive load. So I have drawn E2.
So it should be minus E2, not minus E1.
Where?
On positive y-axis.
This should be.
So you told it is minus E2.
No, I think it is E1. I have told, but I have written it correctly, I guess. Let us check the equations once more. No, it is minus E1, sorry. So not E2, E1 only it is. So see, E1 and E2 are same only, na? Equal in magnitude, na? So if I draw minus of E2 or minus of E1, it means the same only, correct?
Yes.
Yes.
Yeah, so it's minus E1 only. So V1 is I1 R1 plus I1 X1 minus E1. Okay, and here on this side E2 is V2 plus I2 R2 plus I2 X2, and here I1 is I0 plus I2 dash. So these three equations, with the help of these three equations, we can plot. Now the phasor angle between, we have to determine the phasor angle now. So angle between phi 2 is angle between V2 and I2. We have already shown. Then phi 1 is the angle between V1 and I1, which is over here. So this is phi 1. And phi naught is the angle between V1 and I naught. Okay, so where it is? Over here, from here to here. So this is phi naught. Alright, so this becomes my phasor diagram for a practical transformer. It's not at all hard. But now you have drawn it 3 times. Do you see it's hard enough? No, na? It's very easy once you understand it. Okay, everyone understood? So if this comes in exam, please don't leave it as an option. It's easy enough if you practice 1 or 2 times more. Understood? Can we move on to the next one now? We want to complete transformers today, or we'll do it next time then? Complete it today, right? Because we have completed this. This was lecture number 42 contents still, which we should have completed a long time back, but still. So we have half an hour into today's lecture. So I think we'll complete the transformer module. What do you say? Okay. I hope you will draw the phasor diagrams properly and you have understood these equations along with the practical circuit of the transformer. Each and every term is clear to you. R1 and R2 are the winding resistance, X1 and X2 are the leakage reactance at the primary and secondary, and R0, X0 are the result of IW, I mu, which is the result of open load transformer, current due to open load transformer. Okay,
Yes, sir.
so now we have completed this part also. I'll mark it yellow. So you're left out with voltage regulation and efficiency of the transformer. This will go fast a little because we have to write very less over here. So this will be, yeah, from now our lecture 43 starts actually. This was done last year. You can see the date and time, but we are using the same document. And last time also that this was the 43rd lecture only, which I've taken extra. So I've completed this in one go as a lecture number 43 last time. 28, 4, 24. All right. Let us see now quickly transformer ratings. So there are write down the topic as transformer ratings, please, in your books. I'll make you write the main topics. So there are two types of ratings for the transformer. One is the voltage rating and other is the kVA rating. Kilovolt ampere. Okay? Voltage rating and kVA rating. Understood? Now, voltage rating indicates the normal or the rated primary and secondary voltages. So, for example, for the voltage rating given as 200 400 volt, that means the primary rated voltage is E1, which is approximately equal to V1 is equal to 200, and secondary rated voltage is E2 V2 is equal to 400 volt. Understood this? Voltage rating normal. These voltages are in RMS, huh? Remember it. This primary or voltage ratings are in RMS, not in peak value. Then the KVA rating. So during the operation of the transformer, the power losses takes place in the winding and the core of the transformer, right? These power losses appear in the form of a heat, which increases the temperature of the device. The output of the transformer is expressed in kilovolt ampere. Okay, the rated transformer output is limited by heating, and hence the losses in transformer are copper and core losses. So these losses depend upon the voltage and the current, and almost unaffected by the power factor of the load. Therefore, the transformer rated output is always expressed in kVA and not in kilowatt. All right. So what I'm saying is, these losses depend upon the current and the voltage and are almost unaffected by the power factor. Now, what is the actual power formula? Vi cos phi, right? And now we are saying that in a transformer, the losses depend upon voltage and current and not on the power factor. So, which power factor? I mean, which power has the formula V into I? S, right? Apparent power. Yes or no? And apparent power का unit कितना है? Volt ampere. That's why we don't use kVA, kilowatt. In transformer we use kVA. Understood this? Hello.
Yes.
See, active power in a single phase circuit, it's Vi cos phi. Now we are saying कि a power factor of the load is independent of the losses. So the apparent power will be V into I. This is the power which in kVA rating of the transformer. Okay. So if we want to convert VA rating into KVA rating, so E1 voltage E1, EMF voltage E1 into I1 at full load. Here it is KVA rating is given by E1 into I1 at full load divided by 1000 is equal to E2 into I2 at full load divided by 1000. So I1 I2 full load means full load primary and secondary current. Okay, so VA into KVA can be written as, the if you want to write KVA rating, you divide by 1000. So let's say your KVA V into A is 1000 volt ampere. So how many kilovolt ampere? 1 kilovolt ampere. Yes or no? So 1000 you divide by 1000, you will get 1. So it will be 1 kVA. Understood this? This both are the same. If it is 5000, then that will be 5 kVA. Okay. Now from the kVA rating, we can calculate the full load primary current and of the secondary and the primary winding. So I1 full load will be kVA rating, which will be available in the data sheet of the transformer, into 1000 upon E1, and I2 full load will be kVA rating into 1000 upon E2. So knowing the kVA rating, knowing the EMF induced E1 and E2, we can find the primary and the secondary current at full load. Understood? Can we go for voltage regulation? Yeah, students.
Yes, sir.
So write down the topic voltage regulation in your in your books. Okay, I'll remove this thing. The voltage regulation of a transformer. Can we start? So this is my practical transformer. Okay, we have I2 E2 where V2 is not equal to E2 in this case. For an ideal transformer, the voltage regulation should be 0. That means it should not, output voltage should not vary much. Okay, so when a transformer is loaded, the secondary voltage reduces. Why? Your E2 will no longer will be equal to V2, right? Because some drop will be there across the resistor and some will be taken by I2 V2, I2 into X2. So E2 is equal to I2 R2 plus I2 X2 plus V2. So that is what we are saying over here. When a transformer is loaded, the secondary voltage reduces. All right, due to the voltage drop across the secondary winding R2, winding resistance and the leakage reactance. This change in the secondary voltage from no load to full load condition is expressed as a fraction of no load secondary voltage, that is the regulation of the transformer. Okay, so write down this formula. Percentage regulation is secondary voltage on no load minus secondary voltage on full load conditions divided by secondary voltage on no load. So secondary voltage on no load is written as E2, voltage is E2. Secondary voltage at full load is V2, and secondary voltage at no load is again E2. So percentage regulation is E2 minus V2 upon E2 into 100. Understood? Now, the output E2 EMF induced, mutually induced EMF E2 depend upon the magnitude of the load current and the nature of the power factor of the load. So therefore, voltage regulation is a figure of merit of a transformer. The smaller the voltage regulation, the better is the performance of the transformer. That means difference between E2 and V2 is smaller, the better is the transformer regulation. Can we go for the expression of voltage regulation now? Students, you have understood the definition? Yes?
Yes, sir.
Alright, let's go. So no need to write these things, but just listen. So this is the simplified equivalent circuit of the transformer with the resistance referred to as secondary, with the resistance and reactance offered to the secondary, as you can earlier shown that this we can show that R1 plus X1 will be transferred to the secondary side by multiplication of K square. So RO2 will be R2 plus K square R1, XO2 will be X2 plus K square X1, and ZO2 will be uh, square root of R over RO2 square plus XO2 square. This we have seen already. Now the phasor diagram of the secondary side of the equivalent circuit for lagging power factor is given as follows. This is the phasor diagram. You can draw it on your own. So here E2 is I2 RO2 in this case. E2 is I2 RO2, I2 XO2 plus V2. So that is what we have drawn over here. Here E2 will be equal to V2 plus I2 RO2 plus I2 XO2. So that is E2. We have seen this before. And E2 and V2 has a relationship of phi because it is a lagging power factor. Did you understand this power phasor diagram? We have drawn this just now. But oriented towards negative side, but this is positive. It's fine. Yes or no? Did you understood this?
Yes, sir.
Okay. So now in order to find the approximate formula for voltage regulation, the phasor diagram is modified as follows. See, it is modified as follows. We have included geometrics now. So from 0 to A is my V2, A to D is my I2 R2 car adjacent side. Okay, and here we have marked M, B, L, which is a rectangle, and here we have L and C. Okay, so here AD, what is AD? AD we can write it as I2 RO2 cos phi 2. Correct? Yes or no? And BL is again the opposite of the hypotenuse, so it will be written as I2 XO2 sin phi 2. Understood? This is adjacent side, this is opposite side. AD is the adjacent side here, this one, adjacent of this. So it will be I2 R2 cos phi 2. and BL is the opposite side of hypotenuse, I2 XO2. So this BL will be I2 XO2 sine phi 2. Did you understand these two statements for this geometry? Yes or no?
Yes, sir.
Okay. So in this modified phasor diagram, what is E2 minus E1? Or what is E2 minus, sorry, V2? It's OC minus OA, right? Correct? That is same as OM minus OA. Do you agree on this? Because if this line OC falls down, it is same as OM. Yes or no? If this goes down, this C point goes down, it reaches M, right? So OC is equal to OM. Do you agree on this? And OA is OA only. Hello, come on. Yes or no?
Yes, sir.
Acha, tell me what is OC minus OM OA AM? Yes or no?
Yes.
This much. This and this AM. And what is AM? AN plus NM.
Yes, sir.
So NM, as you can see, it's quite small. So approximate voltage drop, we have considered it as AN. So what is AN now? AD plus DN. Yes or no?
Yes.
And AD is what? I2 RO2 cos phi. Cos phi 2, actually we should have written here cos phi 2. And DB is DN is BL only. Same now. So I2 XO2 sin phi 2. Here you write phi 2. I guess I forgot to written over there earlier. This is phi 2. This is also phi 2. These all are phi 2. So the percentage load regulation will be ADBL, that is I2 RO2 cos phi 2 plus I2 XO2 sin phi 2 divided by E2 into 100. So please write down this formula. No, wait. It should be, yeah, plus. ठीक है. Fine, it is fine. For lagging power factor, it is fine. Similarly, for a leading power factor, the approximate voltage will come out to be this. This can be proved later on. We can check it out from the geometry. You can again draw the geometry and check whether this is coming or no. So in this case, the difference between the formula number 7 and here is exactly the same, only the sign will be minus. That's it. So the percentage root regulation for the leading power factor will be I2 RO2 cos phi 2 minus I2 XO2 sin phi 2 into 100 divided by E2. Alright? Return the formula. So the in general, the voltage regulation is given by I2 RO2 cos phi 2 plus or minus I2 XO2 sin phi 2 divided by E2 into 100. Where plus sign it is for lagging power factor and minus is for leading power factor. I hope you are following this, the modified formula for the approximate power voltage regulation. Yes or no? Because now we are going to start with the last topic for this module, that is transformers, which is efficiency of transformers. So can I start?
हाँ
Yes,
सर.
Yeah. So efficiency is defined as the output power to input power. So efficiency is output upon input power. But input power is basically output power plus total losses. Now total losses can be copper loss or iron loss. Okay. So your output percentage efficiency will be output power is divided by output power plus copper loss plus iron loss into 100. Okay. So write down this the formula wala this in the box, expression in the box given to you. Write down that formula. It's output power upon output power plus copper losses plus iron losses into 100. And Wi is iron loss, WCU is the copper loss. Now, for a transformer, output power is given by V2I2 cos phi 2. So we can write in kilowatts as V2I2 cos phi 2 divided by 1000. Agree? But what is cos phi 2? Cos phi 2 is the power factor. So if you want to write output power in kVA, I have to remove this cos phi 2. So once I remove this cos phi 2, it becomes kilo VA, kVA. So output power is given by kVA rating into power factor. That will be in kilowatt. Agree?
Yes, sir.
So also the copper losses is given by I2 square into RO2, and iron losses is I mean WI, right? So WCU is I2 square RO2, and this is WI. So percentage efficiency will be output power divided by output power plus total losses. So write down this modified formula number one. So percentage efficiency will be this will be into 100 is not written into 100. Okay, so it will be V2I2 cos phi 2 divided by V2I2 cos phi 2 plus WI plus I2 square RO2. Okay, now next, I hope you have written formula number one, equation number one. Now we have to derive the condition for maximum efficiency. So maximum efficiency is reached when we get the maximum load current, I2 max. Where if I have a plot of I2 versus efficiency, my efficiency will be maximum when my I2 max will be maximum. So we can start, right, this condition for maximum efficiency. Hello, can we go ahead or you're still
Yes,
writing?
sir.
Okay. So the load current I2 at which the efficiency attains the maximum value is I2 max, and the maximum efficiency is called as eta max. Now this equation number one, you just do what is differentiate both the sides with respect to I2. So this is your equation number one, right? So let us treat this numerator term as u and denominator term as v. So what is the differentiation of du by d by dx of u by v? It is v du by dx minus u dv by dx by v square, right? So we have written v over here. Du by dx will be this v2 I2 cos phi 2 because we are differentiating with respect to I2. So it will be v2 cos phi 2, then minus u, which is v2 I2 cos phi 2 into dv by dx. So
Sir,
yeah,
sir, ये derivation आएगा.
uh, they might ask you in the exam. Yes, that's why I'm doing it. They might ask you, we never know. See, there are few topics now. See, today I've discussed about expression for voltage regulation. They might ask you this in the exam, but that is a big might. Okay, mostly they prefer for this thing, the phasor diagram or the losses in the transformer. This is just pretty advanced stuff, but yeah, we never know, and that's why I'm covering it for to be on the safer side. So let's say for condition of maximum efficiency, let me cover it and then we'll come back to you. Okay, so this is u, this is v. So v were over here, u into dv by dx. So dv by dx will be this term will be there because derivative of this wi will be constant because that is not dependent, and for this will be twice I2 RO2. Here it is. So v2 I2 plus twice I2 RO2 and divided by v square. Understood this? I've written mathematically how to do it. And then for a maximum value, you equate d eta by di2 is equal to 0. So equate this entire equation equal to 0. So this denominator term will disappear. So what will happen is now v2 cos phi 2 and v2 cos phi 2 from here will disappear. What is left out? v2 cos phi 2 plus wi plus I2 square RO2 is equal to v2 I2 cos phi 2 in plus twice I2 square RO2. So here V2 I2 cos phi 2 gets cancelled, and what do we have? Wi is equal to So this becomes over here. So it will Wi will be equal to I2 square RO2. That is equal to copper loss. Therefore, the condition to achieve maximum efficiency is iron loss would be equal to copper loss. Wi is iron loss, na? That should be equal to copper loss, which is I2 dash RO2. Okay? So this is the condition for maximum efficiency. Therefore, when the copper loss is equal to the iron loss, the efficiency of the transformer is maximum. Understood this? Hello?
Yes, sir.
Yes, sir.
Now, the current at Emax will be given by, see, Wi is I2 square RO2, but I2 is I2 max and eta is eta max. So I2 max square RO2 will be equal to Wi. So I2 max will be square root of Wi upon RO2. So this is the maximum value of load current, okay, at max value. So what will be the maximum efficiency? Maximum efficiency is given by output power upon output power plus copper loss plus current plus iron loss into 100. Output power is normally kVA into power factor. So again, output power is kVA into power factor. Now copper loss and iron loss should be same, right, at maximum efficiency. So we are substituting twice Wi into 100. So this is the formula for maximum efficiency obtained uh, for a transformer. It's kVA rating into power factor divided by kVA rating into power factor plus twice iron loss. Wi is the iron loss. All right. So with this, we complete the topic which was called as the voltage regulation and the efficiency of the transformer. And with that, we completed module number 3.1 of electrical machines.